Can you please share the screen?
I think I have shared using Team.
Yeah. Thank you.
Not working. Okay. A minute. Video.
Okay.
We can see you now.
Thank you.
Thank you. Please start.
Thank you. Okay. So thanks for the invitation from Paris, and today I will give a talk about the application of quantum computer to the high energy physics, and this is a very preliminary task to extracting the particle mass on the in the high energy physics and I will talk about how to extract the particle mass on using the quantum computer, and I will introduce the state preparation and measurement algorithm that we proposed recently. And my name is Xiaoyang Wang from Recon Items. Our work is collaborated with Longxiong, Xia Cai, Xiao Yuan, and Yuexin Su and Tongyang Li from Peking University. Let's have a pointer. Okay. Can you see my pointer?
Yes.
Okay, great. First, I will introduce why we use the quantum computer in high energy physics. The quantum computer can be used in many fields in the classical problem. For example, in the Max-Cut problem to study the phase transition, the lattice gauge theory, the drug design, machine learning, or the quantum chemistry. Usually, this problem can be solved using classical computer. For example, using the Monte Carlo method. The Monte Carlo method performs. We need to perform this high-dimensional integration by transforming this integration into a finite sampling of configurations sampled from this Boltzmann distribution. However, in the classical Monte Carlo method, people usually face the same problem, which means that in this classical action, because this action is a complex number, we can decompose it into the S1 and the IS2. Because this imaginary component, this makes the this Boltzmann distribution highly oscillate, such that the sampling from this highly oscillated distribution is almost impossible. However, in the high energy physics, this imaginary component is frequently met. For example, if we want to simulate the real-time dynamics to study the thermalization or the scattering process of particles, or we want to study the QCD phase diagram, or we want to extract the particle mass, or we study the strongly correlated system with many-body interaction, including the chemistry problem and the condensed matter physics. We usually use this method as strongly correlated electron interaction. This is the phase diagram of QCD of the QCD model, where the vertical axis is the temperature and the horizontal one is the baryon density. For example, our natural world, which is as shown in this periodic table, it is included in this phase diagram as shown in this small region. If we have if we want to study this QCD phase diagram and to calculate the mass of these elements in the periodic table, we will face this same problem, which means that if we want to calculate the mass of hydrogen or helium, it would be easy. However, if we want to calculate the mass of more heavier particles, it will be more and more difficult. This is a same problem that we see that there is a sorry. Yeah, you can see that there is a scaling increased exponentially with this number of protons and neutrons. So the time complexity increased exponentially with their mass. However, quantum computer provides us another probabilities to solve this same problem, because in the classical action, this S is usually a non-Hermitian number because it includes this imaginary part. On the other hand, the quantum computer usually use a Hamiltonian to perform the calculation, and the Hamiltonian is a Hermitian operator, such that there is no sign problem in the quantum computer. And additionally, the quantum computer is very natural to perform the real-time evolution because the natural evolution of a quantum system follows this Schrödinger equation. So for the real-time dynamics to study the thermalization and scattering, it has no theoretical problem. So our rest task is to ask if we can study the QCD phase diagram and extract particle mass on the quantum computer. So this is our motivation, and I will introduce the procedures of how to extract the particle mass on quantum computers. On quantum computers, as one of the methods to extract the particle mass is to measure the two-time correlation function, which is the as shown in this over there. This is a function as a function of time t. And after the Fourier transformation into the frequency domain, we can transform this function into this linear combination of this delta function, and the position of this delta function is the En minus E0, and this is exactly the particle mass that we want to obtain. And so our task is to measure this two-time correlation function in the time domain. So on quantum computer, we first usually prepare the initial state into a product of zero state, and then we perform some state preparation algorithm to prepare the ground state of this system Hamiltonian. Then we excite a particle from the vacuum by applying an O-dagger operator, and then we propagate this particle in the real time by e to the minus iht, and which is achieved using the quantum simulation method. And finally, we perform the measurement to measure the expectation of the operator O hat. This propagation method, this propagation procedure can be simply imagined as a sine function, as shown in this red line. And after performing the Fourier transformation, this sine function corresponds to a delta function. And in this talk, I will first introduce the quantum simulation method, and then we go to the measurement method, and finally we will talk about the state preparation method. So on the time evolution is achieved on quantum computer, usually using the analog quantum simulator and the digital quantum simulator. For the analog quantum simulator, we usually construct a system that resembles the target system, Hamiltonian H. For example, in the Rydberg atom array, we usually make the Hamiltonian is resembled to an Heisenberg XY model, as shown over there. And in the digital quantum simulator, we have more degree of freedom to choose the Hamiltonian because we can perform the total decomposition. We first decompose this real-time evolution into several pieces, where each of the pieces is a summation of this Pauli operator. For example, this is an example of 2-qubit Pauli operator, and then this summation can be transformed to this product, and each pieces of the product e to the minus I a sigma I delta t can be realized by decompose into Pauli gates and the CNOT gates. The benefits of analog quantum computer is it can be noise. It can be more robust to noise, but we have only problem-specific Hamiltonian. And on the digital quantum computer, the degree of freedom of Hamiltonian is more universal, but it would be more resilient to the noise. It is more sensitive to the noise. Sorry. And then we introduce the measurement method. If we want to measure this two-time correlation function on quantum computer, we usually use this Hadamard test method. To measure, for example, to measure this two-time correlation function, we note that this two-time correlation function is a complex number. However, the quantum computer can only measure the expectation values, which is a real number. So the Hadamard test method measures the real and imaginary part separately by introducing ancilla qubit, which means we first prepare the ancilla qubit into a plus state, which is a 0 and a Hadamard gate, and then we perform a control operation to the system, and then evolve it, and then measure the expectation of X tensor A and Y tensor A. This X tensor A gives rise to the real part of the two-time correlation function, and Y tensor A gives rise to the imaginary part, and their summation is exactly the two-time correlation function. This picture can be also generalized to arbitrary two-time correlation, arbitrary n-time correlation function, as proposed in this work in 2014. However, applying this circuit to the near-term quantum computer is very challenging, because if we have an analog quantum computer, this control operation actually is not very straightforward to be realized, because the control operation is usually regarded as a digital operation. But for the digital quantum computer, usually this interpolator OI is applied across all the spatial sites. For example, this is the OI is a momentum definite operator. Which means, so to apply this control operation, the ancilla qubit should be connected with the whole system. And this is very hard to for the near-term quantum computer with a very sparse connectivity. For example, this is a qubit connectivity in the IBM's device, and its connectivity is very sparse. And more importantly, we think that the ancilla qubit is not natural in the quantum algorithm, because there is no ancilla qubit exist in the nature. So this inspired us to design an algorithm measurement method without the ancilla qubits. So yeah, if you have any questions, you can interrupt me anytime.
Yes, I have one question.
So
the circuit that you just showed is for the digital quantum circuit, right? Because the analog is different.
Analog, but I mean but if we want to, this is the algorithm. But if we want to measure the two-time correlation function, the analog should also perform this control, right? I mean, by converting the control into some other operations. Yeah.
That is for both analog and digital.
Analog digital platform, you mean?
Using the same circuit, right?
Yeah, using some circuits. Yeah. Yeah, I mean, for example, on the analog quantum computer, we could realize maybe the rotation of ZZ operation, and this rotation of ZZ can be somehow converted to the control operation, but not very straightforward to realize. Yeah. Okay, maybe I can continue. Okay, so in our measurement method without ancillary qubits, we can directly measure this nested commutator and anti-commutator, which is denoted by this bracket with the minus to be commutator and the plus to be anti-commutator. So this is the measurement method that we introduced in our work. We first have this initial state phi, and then we introduce the real or imaginary time evolution of the particle interpolator, e to the minus I00 and e to the minus 00. And this imaginary time evolution is introduced by Mota's work in 2020. And this measurement circuit is consistent with our original picture to measure the two-time correlation function, where this induce of pulse is exactly to apply this O-dagger operator. And compared with the original Hahnemann test method, we find actually we just replace the original control operation into this real or imaginary evolution pulse, so that we don't have to we can eliminate this control operation and the ancillary qubit. To see whether our method can be used to measure the commutator and anti-commutator, we take this simple example of two-time correlation function. We first prepare this initial state. Okay, sorry. Yeah, okay. We first prepare this initial state phi, and then perform this imaginary and this real-time evolution of e to the minus tau 00, and this tau is the duration of this evolution. And we see that this expectation is exactly the and we can measure this expectation from these circuits, and then we can perform a partial derivative with respect to tau, and taking the tau to 0, and we can derive this commutator. And similarly, by performing this anti-commutator, we can by performing this imaginary time evolution, and its derivative gives rise to the anti-commutator. And if we plus this anti-commutator and the commutator, it will give rise to the two-time correlation function. And on quantum computer, if we want to accurately calculate this partial derivative, we can simply use the finite difference method. However, the finite difference method would introduce a very large truncation error. In our work, we propose to use the we introduce a parameter shift rule to calculate this partial derivative more accurately. This parameter shift rule performs the real-time evolution by tau equals to pi over 4 and tau equals to minus pi over 4, and their difference give rise to the accurate partial derivative. And additionally, our method can be naturally realized on the digital analog quantum computer, which is fastly developed in recent years, which means that in our method, we don't have to turn on and off the native evolution of the quantum system of the analog quantum platform, such that the measurement will be very robust to the noise. Okay, so I will demonstrate our algorithm by the numerical simulation on the IBM's quantum device. We first measure the Hadron mass of the Schwinger model, which is the 1+1 dimensional QED model in the high energy physics. And this is the Hamiltonian of the Schrödinger model, which includes the fermionic mass term, the kinetic term, and the electrical energy term. And our simulation is performed on 12 qubits in a one-dimensional chain. where the interpolator is a hadron interpolator equals to psi bar gamma 5 psi. And we measure this two-time correlation function, this hjt and hj0 at time 0, and then we transform this. We perform the Fourier transformation in the spatial domain to measure the two-time correlation function with a given momentum k. And in the right hand, these two pictures compare our method with the Hanma test method. Here to apply this hadron interpolator, our method only apply two CNOT gates, whereas in the Hanma test method, we would need a lot of swap gates for the qubit routing. And our measurement choose the initial state to be the mass to be the ground state of this mass term. And this is approximation to the ground state of the whole Hamiltonian, and we will come back to this state preparation problem later. Okay, so we first simply naively measure the two-time correlation function on IBM Torino, and after the Fourier transformation, we see that this is a hardware result. We see that compared with the noiseless trotter results, there are a lot of peaks at the low frequency domain, which actually is a characteristic of low frequency quantum noise. And to reduce this low frequency quantum noise, we additionally introduce this classical signal processing method. The classical signal processing is frequently used in many fields, for example, including the speech signal processing or the radar signal processing. This is so for the quantum signal measured on the quantum computer, we have two prior knowledge to the signal. The first is that the noise is the short time noise is more reliable because of the decoherence in the longer time is very strong. And the second is that the noise is more random than the signal because the noise usually has no correlation in the time domain. So based on these two prior knowledge, we introduce the signal filtering and the correlation analysis into this classical signal processing procedure, where we first measure this time correlation function for many types, and then we apply the filtering function by introduce a window, and then after the Fourier transformation, we perform the correlation analysis, and then give rise to the output. So this is the hadron spectrum after the signal processing. We see that after we first measure the signal twice on the IBM Torino, and after the correlation analysis and the filtering, we see that the noise in the low frequency domain is much suppressed. And to quantify the effect of the signal processing method, we fit this energy, this energy peaks using this hadron dispersion relation, where this MC square is the hadron mass. And after the fitting, we find that the MC square equals to 1.119, which has a difference to the noiseless trotter result within a relative error of 0.18%. Okay, so this is and this is our numerical results of the measurement method. So do you have any questions?
Yes, I have one question.
Uh-huh.
So what kind of did you use any error mitigation method to?
In this measurement, we use the randomized compiling and the dynamic decoupling to suppress the error.
Okay.
But we didn't use, for example, the zero noise extrapolation, something like that. Yeah.
So how many qubits did you use? 12. Okay.
12. Yeah.
Okay. Thank you.
welcome. Okay, so I will introduce the problem of state preparation now. So in our original method of measuring the two-time correlation function, we simply take the Bayer Wickham omega 0 to be 0, 1, 0, 1, 0, 1. And this is actually different from the true Wickham of the Hamiltonian. For example, in this plot, we see that the overlap between the omega 0 and the omega actually decreased as the system size increased with the system size from 2 to 80. And we see that if we, however, if we want to perform the method on the larger system size, we will see that this, because of the exponential decay with the system size, we will need some method to increase this overlap such that the signal can be measured. For example, if this overlap only decreased is a constant or a polynomially decay, this is okay, and we can measure the signal within a time of polynomial to the system size. However, if the overlap decreased exponentially, and we will need exponential number of measurement to get the signal. So actually, the state preparation method, method is very crucial for us to extract a signal from quantum computer at the larger system size. So our question is that, can we prepare the ground state accurately enough on the quantum computer? So this is we want to study, the reason that we want to study the problem of state preparation. On the quantum state preparation algorithm is used to increase this overlap from exponential to the polynomial scaling. However, for the current quantum algorithm, there is still a very big gap from exponential vanishing overlap to the polynomially vanishing overlap. For example, there are quantum algorithms, including the quantum adiabatic algorithm, the dissipative algorithm, the quantum maritime evolution, and the maritime evolution, and the variational quantum algorithm. However, usually this method requires a very large adiabatic gap, or the Euclidean gap, or the large overlap with the initial states. So, for example, in the adiabatic algorithm, we usually need non-decreased adiabatic gap. However, for many practical problem, actually, it is very hard to derive this adiabatic gap or the Liouvillean gap. So actually, this for many of the state preparation algorithms, there is no performance guarantee to say that we can go from the exponential overlap to the polynomial overlap. However, for the variational quantum algorithm, the variational quantum algorithm have no large enough performance guarantee. So this is a main focus of the rest of our results of the content. So here we study the more simpler problem of the mass cut The so-called mass cut problem is to find a way to cut the maximum number of a graph, and this mass cut problem can be transformed to the ground state preparation of this anti-ferromagnetic Ising Hamiltonian. For example, to prepare this ground state of this Hamiltonian, the QAA problem algorithm is to encode the real-time evolution of this mass cut Hamiltonian on the quantum computer, and this real-time evolution is repeated for p rounds. However, for the QAA, actually there is no large enough performance guarantees, which is characterized by this approximation ratio, which is the alpha equals to the estimated ground state to the exact ground state, and it is smaller than 1. And for the p rounds QAA, we see that the known performance guarantee is 0.79, which has a distance to the best known classical algorithm, and also the classical threshold to be 0.94. And here we propose a new kind of variational ansatz called the Latcon variational ansatz for the Mascad problem. We notice that, for example, in the one round QA method, the quantum gates is arranged in this brick wall pattern, in this even odd and even odd pattern. And in this Latcon variational method, we arrange these two qubit gates along the edge of this Latcon. And here, for the Mascad problem, we introduce the we denote these two qubit gates by this row, this row, and each of the row indicate indicate a zy rotation is e to the minus I theta zy. And this rotation of zy is introduced because this resembles the maritime evolution of ZZ operator of the Hamiltonian of the Mascad Hamiltonian that is introduced by my previous work. Okay, so we can theoretically we can prove that this Latcon arrangement is the optimal of is optimal to derive a higher performance guarantee. So this is the logic chain that how we can prove this optimality. The reasoning is start from that we can have an arbitrary arrangement of the ZZ of the quantum gates. And if we in our article we show that if we want to have the highest performance guarantee, this ZY gate should be arranged with Z right Y left order, which means that for each of the qubits, the Y operator here should be arranged as the left hand side of the Z operator. So if we want to realize this Z right Y left structure across all the qubits, we will find that the quantum gates should not have a directed cycle. For example, it cannot have a orientation of I to K, K to J, J to I, and to avoid this directed cycle, we can naturally derive that this variational gates should be arranged like a Latcon pattern, so that this Latcon VQA is optimal to have the higher performance guarantee. And then this Latcon VQA can be constructed for arbitrary graph with a time complexity of the order of number of edges plus the number of nodes, which guarantees the efficiency of the gate construction. And then we can prove the performance guarantee of the Latcon VQA to be 0.7926 with one layer, and can be further improved to 0.8333 by an angle relaxation procedure. So this, so we see that this single round Latcon VQA is comparable with the 3-round QA in this performance guarantee, and this is the numerical results that we can confirm our performance guarantee.
Is there one question?
Uh-huh.
So what kind of data encoding did you use? And what is the did you try many type of many method of data encoding? And
in encoding, what do you mean by?
You need to encode your data, right? In order to understand your input.
The input is the Hamiltonian, for example, a graph like this. So we just apply each of the ZY gate to each of the edge, each ZY gate to each edge. We just transform this graph into a directed one.
Okay. So the initial one is the plus state, right? It's
yeah. Same to the QAOA. Yeah. just like this. This one.
You show that the light cone VQA is it has a better accuracy than using QAOA with twice layers or something like this, right?
Yeah. We can mathematically show that it has higher performance guarantee compared with QAOA. Yeah. By optimize this gate order into a light cone. Yeah.
Interesting. Thank you.
Thank you. You're welcome. Okay, so we can numerically show, we will then numerically study the performance of this light cone VQA in the later content. Yeah, so first we notice that actually the multi-angle version of the light cone VQA can exactly solve all the max cut problem. Because, for example, if we have this kind of graph, and we can carefully choose the rotation angles to be, if we have known the solution, we can choose the parameter like with this pattern, such that the ground state of the Hamiltonian can be exactly found. However, so that the time scaling of the this multi-angle light cone VQA is transformed to the how many iterations we need for the classical optimizer to find this exact solution. So this is a number of iteration to solution to find the exact max cut solution. We numerically show that up to 50 qubits, that the light cone our light cone VQA has a time scaling, which is a 1.046 to the number of qubits. And compared with the classical method, for example, we compare the classical state-of-the-art classical solver Cplex, and it requires a time complexity of 1.061 to the number of qubits. So this this time scaling of 1.046 indicates that it has a scaling advantage compared with the best known classical method. And then we perform the hardware experiments on the IBM's quantum device. This is a 70 on a graph with 72 qubits and 148 qubits. We show that after some classical post processing, the light cone VQA can exactly solve the max cut problem of the 72 qubits with approximation ratio to be 1. And whereas QAOA with 1, 2, 3 rounds can only reach the maximal value of 0.952. And for this 148 qubits instance, we find that the light cone VQA can reach the maximal approximation ratio of 0.96. Both of these results surpass the classical threshold of 0.94. And additionally, we in the classical optimization procedure, we find that the light cone VQA has a faster convergence to the ground state, maybe smaller than 20 steps, whereas QA with 1, 2, 3, with p equals to 1, 2, 3, needs a larger number of iterations. Okay, so this is the this is all my presentation. So so in this talk, I introduced the roadmap towards the extracting particle mass on quantum computer to calculate the two-time correlation function. And additionally, we discussed about the method to prepare the ground state of the Hamiltonian. But theoretically, it is we still have a very large step to have a very accurate state preparation. And maybe using the light cone VQA, we can have a more accurate state preparation. For example, by have a larger number of rounds to see whether its performance guarantee can surpass the classical threshold. and or the optimize or to choose a better classical optimizer, something like that. And yeah, so this is all my talk. Thank you very much. So finally, I'd like to introduce our Recon Quantum group. This Recon Quantum group is an all Recon activity to foster breakthroughs in quantum computation science, including people from physics, chemistry, life science, humanity, computational science, and information science. And Recon Quantum recently introduced a lot of quantum devices from IBM and from Fujitsu and Quantinum, and we are very welcome that to if you have interest to visit us or something. Yeah, thank you very much.
Thank you, thank you. Oh, please, I have one last question about. It's very interesting your method, like the Lycon method, the VQE. So. In my knowledge, for example, the standard VQE is not warranty the convergency. So, so can you explain a little bit more? So why this result is very interesting?
First of all, I think is you refer to the problem of non-convergence is due to maybe Baron-Plateau problem, right?
Yes.
So in our method of, for example, if you have a constant rounds of Lycon VQA, we can prove that this NS has no Baron-Plateau problem, because for each of the qubits, it only has a constant number of gates applied on it. For example, for this single qubit, you only have 2 gates applied on this qubit. So using this intuition, we can prove that this Lycon VQA with constant rounds has no Baron-Plateau problem.
Yes.
And on the other hand, because of this Lycon structure, actually this circuit is not very straightforward to be simulated using classical method. For example, if you only have this small Lycon, you can simply derive this expectation using the just calculate its backward Lycon. Right? It's just because it only covers 4 qubits. However, for the Lycon structure, if you want to evaluate the expectation of ZZ, you need to consider the whole system size, which is such that the number, the classical resource would increase with the system size. And this is a classical, yeah.
Why the classical resource? I don't get it.
Yeah. I mean, for example, if you want to calculate the expectation of this small Lycon, you will find that you only need to calculate this two. You only need to consider these three 2-qubit gates.
Yes.
Right? And others is just ignored. But for this Lycon, because this ZZ is uncommute with all the quantum gates, right? So you have to consider all of these, the whole Hilbert space.
Yes.
So this it cannot be simulated simply using our classical computer. So this is the motivation that we want to introduce this Lycon VQA, and yeah. So this makes sure that it can be converged efficiently, but maybe is not very straightforward to be simulated using the classical method.
Okay, I have one more question. So by this way, you have to increase the number of 2-qubit gates. Is that correct?
Yeah. The depth of the circuit would be increased with the system size.
So by the way, you have to use twice CNOT gates, and that is the CNOT gate has the highest error rate.
Yeah.
How do you deal with this?
Sorry.
How do you deal with this? Because you increase the number of 2-qubit gates. For example, you use for each gate you use 2 CNOT gates with the rotation Y gates, right? So by the way, you will use a huge number of CX gates, and the CX gate have like 10 times 10 times higher error rates than the single gate. So can you explain a little bit how do you deal with this?
But the QA also has this 2 qubit gate, right? I mean, for the rotation of ZZ also has this, can also be should be also realized using the CX gate.
Okay.
Okay. Yeah. I mean, the number of gates is the same for these 2 qubit for these 2 ANDs, but maybe our depth is more deeper. The circuit depth is deeper.
Yes, circuit depth is deeper, but you use only 1 layer.
Yeah.
Okay. Yeah. Very interesting. Very interesting. Thank you again.
Thank you.
Thank you for this talk.
Hello. Is out?
There are one more question. There are 2.
Yeah. Sorry. Could you explain again how we can implement the imaginary evolution in the quantum circuit? Because you introduced. Yeah.
That's very.
Is it give rise to any quantum overhead when you just have a trade-off between you get rid of a control gate but you add some quantum?
Yeah, for the maritime evolution, for example, in our in our implementation, because the initial state is simply a product state, so the maritime evolution actually is very easy to be realized. On the other hand, if you do not have an initial state to be product state, you would need some. If the initial it is proven that if the initial state has only a finite correlation length, then the maritime evolution can still be realized efficiently. For example, if this finite correlation length is met in the ground state, if you have, we need to prepare the ground state of the system, and usually the correlation length is finite if it is far from some critical point, right? So in this case, you can realize this in maritime evolution efficiently. Yeah.
Oh. Okay.
So if your system is far from the critical point, it is easy. Yeah.
Okay. One more time, and the field operator is unitary.
Field operator.
Yeah,
unitary. Because the maritime it is a quantum in maritime evolution. So the quantum means it is normalized. It is not the whole it is the whole operation is realized by the unitary gate.
Okay.
Yeah.
And one more question. The last question is, what's the reason behind why when the size of the system increases, the overlap between the 2 ground state is decreased? What's the reason behind it?
Yeah, that's actually, this is just our previous results is just a numerical evidence. That in my impression that this exponential decreased overlap is because that you can imagine like this. You choose a bare vacuum is equal to a random chosen from the Hilbert space, because you have no actually you have no prior knowledge about the true ground state. So you only have a random guess. So random guess usually corresponds to a initial exponentially decreased overlap. Yes, I think this is the reason.
Yes, there are 2 more questions from on-site participants, please.
Okay.
Yeah. Can you talk a bit more about your company?
Riken, right?
Riken, yeah.
Okay, he's very interested in Riken.
Yeah. So our Riken Quantum is a newly founded. That it is led by. Do I have the screen shared?
Yes, please.
Led by the Hatsura-san and the Yunoki-san. So if you are interested to Riken Quantum, you can send an email to them. Yeah, this Hatsura-san and Saiji Yunoki-san. Yeah.
To who? To
Yeah. Yeah. You can search for this recon quantum on the website and find their name. Yeah.
All right. So thank you. I have one last question. I'm using QAOA for the quantum optimization problems. Do you think that LICONT VQA can be used for another problem?
Yeah. Sure. I think our construction is can be applied to all the quantum many-body problems, and but we should additionally consider how to, the optimal arrangement. What is the optimal arrangement of the two qubit gates?
Mm.
In our paper, actually, we have a systematic method to derive this optimal arrangement. And for other quantum many-body problem, we can also apply the similar method to achieve that.
Thank you. Very interesting. Thank you for being here.
Okay. Thank you very much.
We're now moving forward to the next talk from Dr. Tianjin Li. He is a postdoctoral researcher in the quantum mathematical science team at RIKEN, Japan, where he works at the interface of high energy physics and computation. He earned his PhD from the Institute of Quantum Matter at South China Normal University. His research focuses on quantum simulation, QCD matter, qubit encodings, Gauss field, lattice Gauss theory, quantum information dynamics. He has contributed to advances in simulating hadronic scattering, extracting the light cone distributions using the quantum hardware, and developing error mitigation strategies tailored to quantum field theory calculations. And today he will talk about quantum simulations of non-perturbative quantities of hadron scattering. Please welcome.
Hi.
Hi. Yes.
Can you hear me? Okay.
Yes, of course.
Okay.
Can you share your screen?
Yes. Wait a moment.
Worry.
It seems I need to
Yeah.
restart the Microsoft Teams. Wait.
Yes. No worry. Chẳng bây giờ gì đâu. Có gì là nó bắt chuyện.
Okay. Sorry for waiting. Now I think I can begin. Can you see my screen?
Yes, you can.
Yes. Okay. Yeah, I can start now.
Yes, please.
Okay. Hello. I'm Tianyin from Weekend Items, and today I'm going to talking about the quantum simulations of non-perturbative quantities in the hadron scattering. And this is the outline of this talk. Firstly, I will introduce some background about the quantum thermodynamics, and then I will talk about how to simulate the hadron scattering process on quantum computer based on the QCD factorization theorem. And then I will introduce how to simulate the scattering amplitude of the hadron scattering process on quantum computer by using the RSZ reduction formula on the quantum field theory. In the second and the third part, I assume that the gauge field has been mapped to the qubit. That is to say, we have translate the language of lattice gauge theory to the quantum computer, and so we need to talk about more details about this in the part 4, and finally I will have a summary. And as we know, there are 4 interactions in our world. They are strong electromagnetic, weak, and gravitational interactions. And sorry, are there any? Yeah, maybe, yeah. And we may ask why we cannot see the strong interactions in our daily life. That is because the scale of the strong interaction is very small. The strong interaction can be probed in the scale of the proton and quark. The scale of proton is about 10 to the minus 13 centimeters, and inside the proton or neutron there are quarks and gluons, and the scale of quarks is about 10 to the minus 16 centimeters. The quark has a label which is named color, and the quark has 6 colors such as blue, green, red, and their anti-color. And the quark interact with each other by exchanging gluons, and that is in the strong interaction. The strong interaction is different from the electric magnetic interaction. That is because the gluon itself has 8 colors. That means the gluon can interact with have the self interaction. However, we cannot see the colored degrees of freedom in our world. That is because the color degrees of freedom is confined. It has confinement. That is to say, the colored particles is confined in the color single object, composite particles, which is called hadron. And there are 3 kinds of hadron. The most simple hadron is the meson, which it contains a quark and an anti-quark. And there is also baryon, which contains 3 quarks, and there is the also the estonic hadron, which contains more than 3 quarks. And the fundamental theory to describe the strong interaction is the quantum thermodynamics. And here is the Lagrangian of the QCD, which is the non-abelian gauge theory. And from this Lagrangian, we can see that the QCD has fermion-fermion-gluon interaction vertex, and there is also the 3 gluon and 4 gluon interaction vertices. This comes from the non-abelian effect of quantum thermodynamics. From the QCD Lagrangian and after some calculation, we can obtain the beta function of QCD, and then we combine with the experimental data, we can obtain the running coupling constant of QCD, and here shows the how the coupling constant alpha depends on the interaction scale, energy scale. We can see that at the low energy scale, the coupling constant will become large. So the QCD has a non-perturbative feature at the low energy scales. This means we need a non-perturbative method to study QCD. nowadays, the most widely used non-perturbative method is the lattice QCD method, which was proposed by Wilson in 1974. And suppose here is the quantum field theory that defined on an infinite volume Euclidean space. Then the expectation volume of the observable can be calculated by this path integral, which can be regarded as infinite dimensional integral. So this can be not simulated on a computer, and then Wilson said we can regularize the quantum field theory on a finite lattice system. The lattice system has a finite volume. For example, is L times A to the 4, and it also has finite lattice spacing between two adjoint lattice sites. And then the observable can be approximated by this finite dimension integration. We may ask, can this method always work efficiently? The answer is no, because this depends on what is the action of a system looks like. If the action looks like the blue curve here, we can simulate this system by using lattice QCD method efficiently. That is because we only need to simulate the fine field from minus 0.5 to the 2.5. And if the action as of light looks like the orange curve here, which is highly oscillated, this kinds of system cannot be simulated using the Monte Carlo-based lattice QCD method efficiently. This is a very famous sign problem of the Monte Carlo algorithm. We may ask which problem will have sign problem if we use the lattice QCD method to simulate it. There are two kinds of such problem. The first kind is the time dependent problem. For example, if we for example, the calculation of the cross section of hadron scattering is such a problem. On the other hand, the finite chemical potential problem is also will also has a sign problem if we simulate it by using the lattice QCD method. Yeah. But those two kinds of problem are very important because they are primary goals of the RIC, LSZ, and other experiments. So how can we overcome the sign problem of the time-dependent and finite chemical potential system? One of the good choice is the quantum computing method, which is a new computing paradigm. So the quantum computer is a computer that uses the physical rules of quantum mechanics to perform the calculations. And there are many advantages of the quantum computing method. Firstly, is controllable, which means we can use the quantum computing to simulate any other quantum mechanical system in our world. This is including the quantum field theory. And the quantum computing can store the quantum states efficiently. Also, compared with the classical computer, the quantum computers can achieve the experimental acceleration when we simulate the time-dependent systems, which means it will not has a sign problem if we use the quantum computing method to simulate the hadron scattering process as well as the finite chemical potential region of the QCD phase diagram. There are two technical routes to simulate the hadron scattering process on a quantum computer. The first technical route is based on the QCD fertilization theorem. And according to the QCD fertilization theorem, we can separate the short distance perturbative phases in QCD with the long distance or non-perturbative phases. So we only need to focus on how to simulate the non-perturbative phases on a quantum computer. This means that we can save our quantum resources. So this technical route is suitable for the near-term quantum computers. There is another technical route. On this technical route, people simulate the hadron scattering process on quantum computer directly. So we can catch all information of the scattering process. But as a cost, we need to spend more quantum resources, such as more qubits and more quantum gates to do this. And then I want to talk how to simulate the how to simulate the hadron scattering process by using QCD fertilization theorem. Here is an high energy collisions process on hadron collisions process inside a collider, and this is incoming proton, and after the scattering, it will produce lots of hadrons in the final stage. And the process of these, the cross-section of this process can be factorized into three parts. They are F and sigma hat and D. And here the F is the non-perturbative parton distribution functions. And these parton distribution functions can describe the internal structure of the initial state hadron. And the sigma hat here is the hard cross-section, and it can be calculated by the perturbative QCD method. And the D here is also a non-perturbative quantities, and it can be used to describe the hadronization of the final state parton. Now I want to show about the operator definition of parton distribution functions because I want to first talk about how to simulate the parton distribution functions on a quantum computer. So here is the operator definition of the parton distribution functions, and we use the label F QH of X to represent the parton distribution function. And its physical meaning is that the probability density to find quark Q inside hadron H with the momentum fraction X. And here the psi bar and psi are fermion fields, and the W here is a Wilson line, and the existence of Wilson line is to guarantee the gauge invariance of the parton distribution functions. Yeah, all things we need to simulate on a quantum computer is the those things inside this bracket, and we denoted these things as F tilde here. So we need to 4 steps to simulate the PDF on quantum computer. Firstly, we need to discretize and map the fermion fields to qubits. And then we need a quantum algorithm to simulate the Wilson line. The hadron state also need to be prepared on a quantum computer. And finally, we need to evaluate the Lie-Cohen correlation functions. Yes, that is because this 2-point correlation function is alongside the Lie-Cohen. Yeah, the N here is the Lie-Cohen is the method alongside the Lie-Cohen. And for the fermion field, we regularized the fermion fields by using the staggered fermion method. In the 1+1 dimensional case, the Dirac fermion has 2 components. And according to the staggered fermion method, we put the first component of the fermion fields onto the even sublattice, and while we put the second component of the fermion fields in the odd sublattice. And then we map the fermion fields to qubits by the Jordan-Wigner transformation. And we see that on the right-hand side of this equation, this is just some combination of the Pauli operators, which can be understood by the quantum computer. And this transformation is this transformation preserves the anti-commutator between the quark fields. This is very important. And in the case of more than 1+1 dimensional, the Jordan-Wigner transformation need to be we need to choose a path to do the Jordan-Wigner transformation. And then we need to deal with the Wilson line on a quantum computer. There are 2 methods to deal with the Wilson line. The first method is we can approximate the Lie-Cohen Wilson line by this GZ Wilson line. And yeah, and in this method, we simulate the non-local Wilson line directly. It means that we need to spend more quantum gates to do this. And the on the other hand, we have another method to deal with a Wilson line, and this method we need to introduce an auxiliary field, which is the capital Q here. And then the Wilson line can be represented by the 2-point function of this auxiliary field. Now we find that the non-local Wilson line is disappeared. We only need to simulate this 2-point function. So in this method, we can use the gate cost of this method will be less, but we need to more qubits to encode the auxiliary field. Then we use the variational quantum eigensolver to prepare the hadron state. That is because the hadron state is nothing but the eigenstate of the Hamiltonian with given quantum number. Here we suppose the quantum numbers of the hadron state is L, and the hadron state is the K excited states with this quantum number L. And so we need that means we need K orthogonal reference state with the same quantum number L as the hadron state as the input state of this quantum circuit. And then we need to construct the answers of the variational quantum algorithm. The answers need to preserve the quantum number of the initial reference state. That is because the initial reference state has the same quantum number as the target hadron state. To do this, we can divide the Hamiltonian into n different parts, and the joined Hamiltonian Hi and Hi plus 1 should not commute with each other, and every Hi need to preserve all symmetry of the full Hamiltonian. That is because we need to preserve the quantum number of the initial reference state. Then the answers can be constructed by the alternative evolution by using those Hamiltonians. Then we can generate a series of tri-wave function by acting the U of theta on the initial reference state. So all of those tri-wave function will have the same quantum number as the target hadron state. Then we need to measure the loss function on the quantum computer. And finally, we need to optimize this loss function on a classical computer, and we need to find the and we need to minimize the loss function and find the solution theta star when the loss function is minimal value. Then the hadron H can be prepared by adding U of theta star on the initial reference state. Finally, we need to evaluate the dynamical correlation function on a quantum computer. The dynamical correlation function can be written as this is given by this formula, and according to the quantum algorithm that proposed in this PRL article, we only need to measure the X-ray qubit, and then we can obtain the real and imaginary part of the 2-point correlation functions. Yeah. Are there any questions here? If no, I will go on.
Sorry, could you explain how you implement the Wilson line in the quantum computer, because it's a gauge field that I have no idea how we So how the gauge field.
You mean how I map the gauge field to qubit?
Yeah, the quantum gate. Yeah.
I will talk about this in the fourth part of this presentation because it is a very long story. Yeah, I just skip here. Yeah, I just assume that the gauge field has been mapped to qubits, and we can deal with the Wilson line like this. Okay.
Okay. One more question. When the mapping from the field, the particle field to the cubic, so it seems like not unitary, right?
You mean which this one?
The Chokran width is not unitary. The field is not unitary, right? So
So
so that means when you calculate the the partition, the parton distribution function, you have to split into different parts and compute them individually.
You are right.
Okay.
Yeah, you are right. Here for the pattern distribution functions, we have two fermion fields, so we need to calculate the x, y, yx, and yy correlation function, and then we add up those results, and then we can obtain the pattern distribution functions.
Okay. Thank you.
Okay, thank you for your question. Yeah. Now, as we know, the QCD is a very complicated theorem. So for the near-term quantum device, we cannot simulate the pattern distribution functions of QCD in the near-term quantum device. To test our quantum algorithm, we need to choose a toy model and then calculate the pattern distribution functions of the toy model. And we choose this toy model, which is named the NJL model. This model only contains a fermion field, and here is the qubit Hamiltonian of the NGL model, and this is the pattern distribution functions of NGL model after mapping to qubits. And this pattern distribution function can be calculated by the exact diagonalization method. So we can use this exact diagonalization results to compare with our quantum computing results, and then we can test the performance of our quantum algorithm. Finally, we execute our quantum algorithm in a classical simulator, and we obtained the final results of the pattern distribution function. In this figure, the solid slide here is from the exact diagonalization method, and the data point here is from the classical simulation of the quantum device. And we can see that the results of those two methods agreed with each other. So this show the correctness of our quantum algorithm. And and we find that the pattern distribution functions has non-zero contribution at the x larger than 1 non-physical region. That is because to the finite value effect of the lattice system. Our result has an expect peak around the x equal to 0.5 here. That is because this peak can be also observed in the QCD global analysis results for the pattern distribution functions. And then I want to talk about how to simulate the hadronization process on a quantum computer. The hadronization of the final state proton can be described by these non-perturbative quantities d. And for different process, these quantities is different. For example, for the exclusive process, we need to use the Lycon distribution amplitudes to describe the hadronization process. While in the inclusive process, we need to use the fragmentation function. So firstly, I want to talk about how to simulate the hadronization of the exclusive process on a quantum computer. As I said before, we need to use the Lycon distribution amplitudes to describe the hadronization of the exclusive process. And here is the form factor of the gamma star plus gamma to pi zero process. And when the collision energy Q square is very high, and the form factor f of Q square can be factorized into two parts, which are T of H and phi. The T of H is the can be calculated perturbationally, and the phi here is the Lycon distribution amplitude. And its physical meaning is the probability amplitude to find a pair of valence quark with the momentum fraction x and 1 minus x inside the meson. And this is also a time-dependent non-perturbative quantity because this quantity is also the Fourier transform of the Lycon two-point function. Here is the quantum algorithms for simulating the LCDA. We see that compared with the PDFs, the LCDAs need to the calculation of LCDA need to calculate the correlator that has different bar state and the cat state. So we need a control D gate here, and the D gate is it can map the reference state of the vacuum to the reference state of the hadron. We also use the variational quantum algorithm to prepare the hadron state and the vacuum state. And the vacuum state can be prepared by adding the U of theta omega star onto the vacuum's reference state, and the hadron state can be prepared by adding U of theta H star on the reference state of the hadron. And then the rest part of this circuit is similar to the circuits for calculating the pattern distribution functions, and that is because we only need to measure the auxiliary qubit, and then we can obtain the real and imaginary part of the Lycon distribution amplitudes in the position space. And here are our results of the lowest QQ bar bound state quark Lycon distribution amplitudes in the NGR model. We also execute our quantum circuit on a classical simulator, and we obtained the QC result here. And the solid line is also the exact diagonalization result, and we can see that those two results are has a good agreement with each other. And we also can see that our result converges to the asymptotic result 6x times 1 minus x in the weak coupling limit. And the peak of LCDA gets narrower when we increase the hadron mass. And this is because the relative velocity between the quark and anti-quark inside the hadron will be less if the hadron mass become heavier. And for the inclusive process, the hadronization can be described by the fragmentation function DIH of Z. And this fragmentation function is the probability density of finding a color neutral hadron H of the momentum fraction Z inside a colored parton I. And this Feynman diagram is the diagram of the semi-inclusive elastic inelastic hadron deep inelastic scattering process, and the hadronization of the final state quark can be described by this fragmentation function. And nowadays, the only reliable way to extract the parton fragmentation function is the QCD global analysis, which means the first principle calculation of fragmentation function is still missing. That is because we can. That is because the fragmentation function is also the Fourier transform of the Lycon correlation functions. And what's worse, we see that there here is a semi-inclusive hadron operator inside the operator definition, and the sum over X is sum over all possible multi-particle unknown states. And this summation has exponentially large number of terms. So it is back challenge to simulate this summation on a classical computer. However, on a quantum computer, we can see that we can see that there is a good way to define X and handle sum over X on quantum computer. That is because the sum over X can be regarded as the identity operator of subspace in the Hilbert space of the quantum computer. According to this, we proposed a quantum algorithm to simulate the fragmentation functions on quantum computer, and the quantum circuit inside these brains is the semi-inclusive hadron operator. So we can see that we do nothing here for these qubits. These qubits we do nothing. That is because sum over X contributes to as the identity operator of this subspace. And here we do something here. That is because we use those two qubits to represent the wave packet of the final state hadron. We also use a variational quantum algorithm to prepare the hadron state, and on the output of the quantum circuit, we only need to measure the X-ray qubit, and then we can obtain the fragmentation functions. Here are our results, and we also execute our quantum circuit on a classical simulator, and we find that our result has qualitative agreements with this PRD article. And in the third part, I will talk about how to simulate the scattering amplitude directly on a quantum computer by using the RLZ reduction formulas. The first quantum algorithm to simulate the scattering amplitude on a quantum computer was proposed by the Jordan, Lee, and Qiskit in this Science article. There are there are five steps in this JLP algorithm. Firstly, they need to prepare incoming particles with widely spread wave package, and in this during this they need to turn off the cupping constant, and then they need to adaptively turn on the cupping constant, and there will be some interactions happened, such as some scattering between the particles. And then we need to adaptively turn off the coupling constant, and finally they need to measure the results and then obtain the cross-section or scattering amplitude of the scattering process. And however, there are two non-ID features of the JLP algorithm. Firstly, because we need to prepare the wave package of the incoming particle, that means we need to cause lots of qubits to do this. And also the adaptively turn on and turn off the coupling constant will require a long time span of evolution, which means we need to cause a lot of gates to do this. Yeah, there is another thing is that they prepare the incoming particles with turning off the coupling constant, so this method cannot simulate the bound state scattering. To overcome those non-ID feature of the JLP algorithm, we propose that we can use the LZ reduction formula to simulate the hadron scattering, the scattering amplitude of hadron scattering on a quantum computer. And suppose we are concerned about the scattering amplitude of K in incoming particles and N in incoming particles and N out outgoing particles, then the LZ reduction formula tells us that the scattering amplitude can be represented by those three quantities. The R here is the field renormalization constant, and here is the on-shell kinetic N in plus N out point correlation functions. And the third part here is the on-shell is the inverse of the on-shell kinetic 2-point functions. Yeah. Why we need to multiply those on inverse of on-shell 2-point functions? That is because the on-shell kinetic endpoint functions will be singular if we put the external net on shell, and this singularity can be removed by multiplying the inverse of the on-shell kinetic 2-point functions, and then we can obtain the finite results of the scattering amplitude. Yeah, all of the those three parts of the all of those three parts can be simulated on quantum computer efficiently. Yes, for example, this R can be calculated by the quantum algorithm which is similar to the algorithms for calculating LCDA, and this endpoint function can be calculated by the endpoint function algorithm that was proposed in this PRL article. And here are some advantages of our framework. Firstly, we need not to prepare the wave packet, and we also need not to adaptively turn on and turn off the coupling, and we can also simulate the bound state scattering in our framework. And here are the results. Firstly, we test the propagator of the composite operator. So the Fourier transform of the propagator has mass poles when the momentum square tends to the mass of the hadron state. We can find this pole structure here, and the position of poles is very near to the exact diagonalization results of the hadron mass. And we also calculate the kinetic 4-point function of the quark fields. We find that when the one of the external lead go to on its mass shell, then we can see that here will be a pole structure. And also for the 2-point function of the quark field, when the quark goes on its mass shell, and there is also here is also the same pole structure here. So this means that we can remove the singularity of the external lead of 4-point function by multiplying the inverse of the propagator. This is very important for calculating the scattering amplitude by using the LZ reduction formula. In the final part, I will discuss how to map the gauge fields to qubits. Yeah. Nowadays, the most popular method to regularize the gauge fields on a lattice is the Kogan-Solsky formalism. And this formalism does not have any gauge fixing. So in this formalism, they put the fermion fields on the lattice, and while they put the gauge fields as on the link between two lattice sites. So in this formalism, they are two constraints. Firstly, is the primary constraints pi0 equal to 0, and there is a secondary constraint which is named the Gauss's law here. And then the Hamiltonian of this constraint system can be represented by adding up the energy of the electric field and the energy of magnetic field, and minus the undetermined A0 multiplied by the Gauss's law operator. And here is the quantization conditions in the Kogan-Solsky formalism. So we will ask a question is, because the A0 here is an undetermined function, so how to remove the inferences from the undetermined function A0? Yes, the answer is that we can use the Gauss's law operator to project to the physical subspace. That is to say, if those states can be annihilated by the Gauss's law operator, and then these states will not. It means that the A0 will not have a contribution to this state, because the A0 is multiplied by the Gauss's law operator. Yeah, and the other thing is that in the Kogan-Solsky formalism, the Hamiltonian should be gauge invariant. That is because they do not do any gauge fixing in this formalism. Which means that the Hamiltonian need to be commuted with the Gauss's law operator. Yeah, because the Gauss's law operator is also the generator of the gauge transformation. Yeah, the if the Hilbert space of the gauge link has infinity dimension, all things in the Kogan-Sutton formalism behaves well. However, if we want to simulate the Kogan-Sutton formalism on a quantum computer, that we need to truncate the Hilbert space of the gauge fields. That is because the Hilbert space of the quantum computer has a finite dimension. So after the truncation, we will find that there is an impossible triangle in the Kogan-Sutton formalism. That this impossible triangle is that we cannot preserve the Gauss's law strictly after digitization, and we cannot have controllable digitization ever, and we cannot have unitary gauge link spontaneously. Yeah, we can find that this impossible triangle can be overcome by fixing to the Coulomb gauge. So we propose that we can do some gauge fixing instead of do not fix the do not choose any gauge. Yeah, we choose the Coulomb gauge, and as a first step, we as a first attempt, we discuss the Coulomb gauge quantum electric dynamics on the lattice, and here after fixing to the Coulomb gauge, the A0 can be determined by this function, and then we regularized the Coulomb gauge QED on lattice by putting the fermion fields onto the lattice of the position space, while we put the gauge fields on the lattice of the momentum space. And then we can write down the Hamiltonian of the quantum electric dynamics here. For each spatial dimension, we have m lattice sites, and here we use the Wilson term to we use the Wilson fermion to suppress the doubling problem of the fermion of the lattice fermion. So we have a Wilson term here. Then we find that we can overcome the impossible triangle of the Kogan-Sutton formalism in our Coulomb in the Coulomb gauge formalism. That is because the Gauss's law can be preserved strictly by solving A0 and the polarization vector of the photon on lattice. And also we can also preserve the unitarity gauge link because the AI is Hermitian operator, so the exponential of A is the unitary operator. Also, our formalism has a controllable truncation error if we truncate the Fock states of photon to the lambda, and then we can estimate the truncation error of the arbitrary wave function of the theory, and we can find that the truncation error epsilon s can approach to 0 when the truncation lambda goes to infinity. So although we can overcome the impossible triangle, but we need to introduce the non-local interaction terms in the Hamiltonian after fixing to the Coulomb gauge. Here are the qubit Hamiltonian of the Coulomb gauge QED. That is to say, we have translate the language of the Coulomb gauge QED to the language of quantum computation. That looks very complicated, but this is nothing but some combination of the Pauli operators. This F, G, or epsilon here are nothing but some coefficients. And here is the summary of this talk. Yeah, thank you for listening.
Thank you. Thank you for the
Thank you.
talk. Do we have any questions? Online audience? Questions, please unmute yourself and ask.
Oh, okay. I have a question. Do you have any truncation? I mean, the cutoff from the gauge field to the cubic system?
Yeah. We do the cutoff. We truncate the Fock state of the photon. Yeah. Here, here the Fock state is just the Fock state because we put the photon fields on the lattice of momentum space. So we use a dagger to describe the photon fields instead of use the gauge potential. Yeah. Here is just the creation and the annihilation operator of photon, and the P here is the momentum of the photon, and the R here is the helicity of the photon. So yeah, we can create more and more photons for a given P and R because we can add the we can add the we can add the A dagger to the vacuum to do this, but we have truncate the Fock state to the lambda, which means that if we add the Fock state with photon number lambda, and then we adding this state by A dagger, we will get 0 here. Yeah, this is the truncation.
So do we have any more questions? Please unmute yourself and ask if you have any more questions. If not, then please join me in thanking the speaker once again. Thank you for the nice talk. And
Okay, thank you.
we'll break this session for the coffee break, and then we'll join again in 15 minutes. So see you at 11:15 Paris time. Thank you. So welcome back after the break. Now we'll begin our session with Dr. Natalia Ina. She's a postdoc at New York University, Abu Dhabi. She's a researcher at the forefront of quantum machine learning and quantum algorithms, currently serving as a research team lead at the EBIIN lab and at a postdoctoral research associate at the Center of Quantum and Topological Systems at New York University, Abu Dhabi. She earned her PhD in quantum machine learning from Hassan University of Casablanca, where her research explored the integration of quantum computing with machine learning to address complex challenges in fields such as finance and cybersecurity. Her work focused on developing quantum neural network, quantum optimization, and federated learning approaches, bridging theoretical advances with real-world application. Beyond her research, she is deeply engaged in mentoring and outreach, helping make quantum technologies more accessible to students and practitioners worldwide. We are honored to have her to give the talk today on Introduction to Quantum Machine Learning and its application. I'd like to join in welcoming Dr. Ina for the next talk. If you can share your slides, please. Are you there, Dr. Ina? I think we lost the connection.
Hello. Can you hear me?
Thank you.
Yeah, we can hear you. Perfect. Okay, so please join me in welcoming Dr. Nualia Inan, postdoctoral researcher at New York University, Abu Dhabi. She is a researcher at the forefront of quantum machine learning and quantum algorithms, currently serving as a research team lead at eBrand Labs and as a postdoctoral associate at the Center for Quantum and Topological System at New York University, Abu Dhabi. She earned her PhD in quantum machine learning from uh, Hassan El University of Casablanca, where her research explored the integration of quantum computing with machine learning to explore complex challenges in fields such as finance and cybersecurity. Her work focuses on developing quantum neural network, quantum optimization, and federated learning approaches, bridging theoretical advances with real-life applications. Beyond her research, she is deeply engaged in mentoring and outreach, helping make quantum technologies more accessible to students and practitioners worldwide. We have the honor of having her today for this talk on Introduction to Quantum Machine Learning and its Application. Will you please share the screen now?
Thank you. Yes, share this. Just once again. Yes, need to share. Okay. Can you see my screen?
Yes.
Okay, I don't know. Okay, right now it's still there, right?
Yeah.
Yes, everything is perfect.
Okay then.
Thank you a lot.
Yes, thank you. Yeah, first of all, thank you for the invitation. Today's talk is about since it will be like the introduction and more details about quantum machine learning, like basic, it will be covered in the next talk. For this one, I will talk about like quantum machine learning models and how we can use them in different application. And based on the time, I might tackle like one of the application in details. So first of all, like quantum machine learning as a definition is like a research area that explores the interplay of ideas like from quantum computing and machine learning. We use both like the theoretical side from quantum information, quantum mechanics, then the way how we train the model and different approaches comes like from computer science and machine learning. And how it started, or how it works. So we have the qubits, which is like fundamental units of quantum information, and to manipulate them, we use quantum gates. This is there's operation that we can use like superposition or entanglement. And then from this gate, we can integrate them and develop a quantum circuit. Now, how to make this quantum circuit as like for quantum machine learning model? So it's just like use this quantum circuit to perform a machine learning task. But another thing is like the parameters that inside this circuit should be trainable or tunable. So this is what we want to do in quantum machine learning. It's similar to classical. It's just like instead of the way, think of it like the parameters of the gate. For example, the rotation, angles, and etc. So this is in general. Yeah, this is how it works. So of course, like there is a huge part just coming from the classical side. So we have a data set, we do the pre-processing, feature engineering. Once we have the features and the label ready, we pass them to the first step, which is data encoding. we just convert this data from the classical form to a quantum, which is in form like of a quantum state. And this is done also like using a quantum circuit. Then after that, we do the post-processing using quantum circuits, which is like the trainable quantum circuits. We call it like trainable quantum circuits, parameterized quantum circuits, or ansatz. Then we do the measurement output. Then we have some, like we calculate the loss when we do some iterations to update the parameters using classical optimization or classical optimizer. Yeah, and this is probably, it will be in details in the next talk. So I will just like jump to the algorithms. So there is the fully quantum machine learning and there is the hybrid quantum machine learning. At this, like there is like two different definitions. Sometimes like if we say like fully quantum, it means that everything is quantum. And as I mentioned earlier, like we have the classical optimizer part. So this is not fully quantum. But sometimes like it can be, this is like we call it just quantum. It means like everything is quantum, but the optimization is done classically. For the hybrid, it's the same. Some like researchers say it's like because of the optimization part, it's still hybrid. And hybrid has another definition, which means like adding some classical layers at the end and sometimes at the beginning. So it's not just a quantum circuit. We have classical layers, like dense layers, fully connected ones. It depends, like all the researchers, like sometimes they put it as fully or hybrid. For now, it was just like quantum machine learning models. Yeah, and there is like, this is also another thing, the optimization part. Sometimes it's covered in the model, sometimes it's like another field. But yeah, there is like different algorithms. So there is the quantum approximate optimization, and there is variational quantum eigensolver, quantum annealing. Just these two or the three, they have a lot of variants. Like every time there is like just a changing of the loss function, changing the way how you formulate the optimization problem. So there is like plenty of these variants of this algorithm. And then we have the quantum kernel space, which is quantum supervector machine and like quantum clustering as a task. We can use like k-means, quantum k-means, and different ones. Then we have like, this is generative model, quantum autoencoder. Then there is like quantum neural networks. It can be used like for too many models coming from the classical side, just the quantum parts, quantum convolutional, quantum recurrent neural network, quantum generative adversarial networks. It's the same. It's also like a generative model, like quantum Boltzmann machine, etc. Then we have the parameterized quantum circuits, which is the backbone of all these models. Now I will just like explain a few of the models, starting with quantum perceptron. So in classical, one of the first model of machine learning was perceptron. So that's why I would say it's easier to start with this model, which is kind of like an analog, a quantum analog of the classical. It's designed to use quantum gates and circuits to perform binary classification tasks. And it extends the capabilities of the classical perceptron by using this like quantum principles in general. Yes, and this was like yeah, how it works. It's almost the same. We have like quantum gates or unitary gates, U theta. Then we try to manipulate the input qubits. This qubits or these gates apply unitary transformation to encode the data into quantum states. Then the qubits initially in the zero states are transformed using this gate. Then which are parameterized to learn the classification boundaries. And here in this, there is like an ancilla qubit. This helps like in the processing and measurement stages, but it depends. Yeah, and on the right side, this was like a specific implementation of a quantum perceptron circuit. I think one of the first, the first practical implementation. They use like different layers of quantum gates applied to the input, Hadamard, Z gate, X gate. Then they have like some parameters, W1, and to represent the weights that the circuit adjusts during the training to optimize the classification task. Then measurement at the end of the circuit provides the output, which can be interpreted as the predicted class label. Yeah, this is how it works in general. But yeah, usually like once, if you want to design a model, it's not that easy. Sometimes you need to change, adjust a lot of parameters. For example, this is one of the first implementation, but the problem in quantum, like you cannot generalize. Maybe they use it, for example, for iris. If you have another dataset and you want to use quantum perceptron, you can start with this implementation, but at the end you will have another implementation or another circuit because you need to adjust it based on your needs, which is like another dataset. So that's why usually on almost all the papers, you will find kind of like a customized architecture. So in general, this is how it works, but like in the implementation side, especially for application, it will be something different. And this is just like one of the example. So this is what we call customized architecture. So we know how it works. Okay, we start from that, then we start adding things. So for example, here we have data encoding. This is amplitude encoding, then an ansatz using like unitary gates. Then here, for example, we added Grover algorithm. So I'm not sure like if you are familiar with Grover, but Grover algorithm is a quantum search algorithm that provides a quadratic speedup for unstructured search problems. And it operates by amplifying the amplitude of the desired solution state, thereby increasing the probability of measuring the correct output. Think of it, you have like a basket of different solutions and like they are all equal. And once you apply like Grover, you can get like a higher probability to find the right solution for your problem, something like that, in simple words. So here the idea is like, okay, we have a perceptron, but it's kind of like slow and the convergence is not happening or the performance is not good. So let's try to think about something. We are like Grover algorithm, for example, and this is somehow reflect in finding the conversions faster. So this speeds up learning process and enhance the probability of the correct output state. So this is one of the, I would say, customized architecture. And of course, we have the measurement and the optimization as I explained. Moving to another model or like function. So quantum kernels, usually in classical machine learning, kernels are powerful tools used in methods like or algorithms like super vector machines and clustering. And the core idea of those kernels is like to map the data into higher dimensional feature space where patterns become more easily separable. So for example, if you have like a 2D distribution of the data and it's very hard to classify it, you can just like use a kernel to make it in 3D space, then it will be easier to separate. Quantum kernel extend this concept by embedding the data into quantum feature space, which we call like Hilbert space. So using the PQC, parameterized quantum circuits, in this space, like the similarity between two inputs is captured by the inner product of their quantum states. And this approach allows us to construct a quantum kernel matrix, which can then be used in classical algorithms as well. And this is the, well, what we call like quantum super vector machine. And I will explain it in the next slide. Then, yes, yeah, but yeah, in the diagram here, so the upper part shows the classical kernel pipeline, data mapped into a classical feature map, then we calculate the similarity with the kernel function. Usually for the similarity, we calculate the distance. There are also other metrics based on the application. Then in the lower pass, as you see here, it shows the quantum data encoded, then overlaps define the kernel values, which is the operator that you need to define. And it can be used for different algorithms as well, because it's kind of like a function. So, and we use it for quantum supervector machine. So yeah, it has the same thing, quantum circuits processing, the encoded data state undergoes transformation via a sequence of quantum gates. For example, here we have G1, G2, 3, 4. Then this processing step is crucial for implementing the algorithm measurement. Then we have the, of course, like the kernel trick, as I explained. Then yeah, but technically most of the time the quantum supervector machine is more about like using the kernel parts as like a feature map, then use another SVM to do the classification, because usually quantum machine learning or quantum classifiers are kind of like weak. That's why most of the time we add some classical layers at the end, like softmax, just to make sure that we have the right prediction or classification. Moving to another model, which is like widely used, the quantum neural networks, it's the same thing. We use like different things. Here we can apply all the techniques that come like from the classical regularization, like dropouts, if we have any overfitting or underfitting. Then it depends also like on the data set. If it is like more complicated or more complex, we add like more layers. Then of course, like the choice of this gate, the choice of the loss function. But the main thing that you need to know about quantum neural network, besides the challenges like barren plateau and too many things, I will explain them later, that if you are dealing with multi-classification, probably you will have to add some at the end some classical layers to do the classification exactly. So the model will do like the post-processing, but like the classifier will be kind of with some classical layers, or just like softmax can do that. Then we have quantum neural network. Quantum graph neural network. So here there is another definition of this model. So sometimes you just like embedding of the quantum of the graph into quantum states, and we call it quantum graph neural network. Sometimes you just like how you use the data, graph data directly into quantum states and do with like a proper quantum neural network. So the definitions or like the implementation differs like from paper to paper. For example, just this is one of the examples. So it starts also like you have a data, then you do feature compression. And here the input graph data undergoes like to reduce the dimensionality while retaining the essential information. Then encoding, as I explained before. And for the data encoding, probably it will be covered in the next, but there is like different techniques. So, and also like the choice of, to find like the best one, you need to try, because like it's not, we have a list by order, this is the best. No, you need to try, and like we cannot generalize. So it's based on the problem, the objective, and the task, and the data set. Then after encoding the VQC, then we have average pooling. As I mentioned, sometimes you need some classical layers to help you do the task, linear layer, then the optimization. But yeah, the objective is to optimize the parameters to accurately map the input graph data to desired output. Another one, which is the quantum convolutional neural network. So usually for the classical CNNs are built upon the convolutional layers for extracting the features of the input, and most of the time are used for image classification task in computer vision. For the quantum convolutional, it extends the fundamental properties of these CNNs, and its structure consists of applying alternating convolutional layers and pooling layers and fully connected layers. It's kind of like hybrid. The convolution operations are performed as parameterized unitary rotation based on the PQCs. Then the pooling layers are used to or for dimensionality reduction. But since in quantum systems it's not possible to directly remove qubits from the circuit, they are implemented by measuring a subset of the qubits and using this measurement to control the next operations. From the implementation side, sometimes it's easier because you do a lot of, you have your data, you do your pre-processing, you do your encoding, then you add some classical layers, then the convolutional, then again just a representation of that layers that do the task of the classical. This one is convolution, and I would just say the name is different. So the idea here is to have a convolutional layer where instead of processing the entire input data with the global function, so a local convolution is applied, and only convolutional layers are implemented with the PQCs. That's why we call them convolutional. And they introduce preliminary layers before the classical CNN to manipulate the input. And it's kind of pre-processing or feature embedding more. So the inputs of the first classical layer is a quantum output measured classically that's preserve a large amount of information. And this is potentially used to improve the contextual feature extraction in the classical layers. But yeah, in the current quantum hardware system, I would say that because of the limitations of the number of qubits and the architecture, so I would say it's kind of valid solution for hybrid networks. Just since low qubit circuits are sufficient to perform the required task, so you can just use that. But it's kind of just the embedding part. You are not doing the task exactly with the quantum, but somehow in adding the quantum can somehow enhance a little bit if you want to use the quantum. Then there is other models like quantum ResNet. So here it's just an hybrid extension of the classical ResNet architecture. So, sorry. Here in the top, we have a classical ResNet pipeline. Some card images are passed through a ResNet 34 backbone. Followed by a series of fully connected layers. These layers progressively reduce the feature dimensions, eventually outputting prediction of car models as for example, Audi or BMW or different ones. And this is the standard deep learning approach for image classification. For the quantum or the hybrid quantum classical ResNet, here the process begins the same way with ResNet 34 backbone, then to extract initial features. However, instead of passing these features entirely through classical fully connected layers, some of them are mapped into a quantum layer. Then, yeah, for example, here they are using Hadamard gates to prepare the qubit, rotation Y, Z, and X, which are like the trainable, then measurement. And here, like the quantum layer can be repeated multiple times, just like to make deeper hybrid structure or like more expressible. Yes, the thing is like based on the paper that they proposed the model, they said like it's somehow like the hybrid design will help combine the power of classical feature structures with the expressive capacity of the quantum layers. So quantum layer can somehow capture coloration and high dimensional feature mapping that might be challenging for classical. Another one, which is quantum recurrent neural network. So they are also inspired from the classical, as I mentioned before, just like the same thing. We are just quantum. And this is just one way to do or to implement the model. There is like plenty of papers that sometimes it's totally different. Sometimes even the idea or like the layer comes like from a quantum learning theory. But here, like we have the recurrent neural networks, layers are replaced by specific types of PQCs, and here we will call them like quantum recurrent neural network. And instead of being dense like the other models, this is like highly structured with a fewer parameters that can be reused, because like applying multiple QRNN cells iteratively forms the quantum recurrent neural network. But the main issue here is the decoherence. But it can be mitigated by implementing multiple QRNN cells in a parallel way. So for example, because like the quantum recurrent neural network or classical, you are using the previous information, and most of the time you're using like for example, when you have like a correlated data or like some text prediction or a video, so you need to know the information before. That's why like the coherence may be a problem for this. But I think like for a small subset of the data, it can be used. There is like a couple of applications that they managed to use this model. Another type of models, which is generative models, like everyone right now is like talking about these models because they somehow they have like some potential comparing to the others, or maybe at least at this stage. So quantum generative adversarial networks, it's the same, comes like from the classical, and usually for classical GANs, they have like a generator that generates new fake data, and the other part is like a discriminator that distinguish the fake from real data that is generated by the other generator. Here, most right now, as far I know, most of the quantum generative adversarial networks are hybrid, because this type of architecture is too large to be implemented fully in quantum. So it's possible to design the hybrid. Either the generator or the discriminator is implemented in classical computing, the other part in quantum, for example, like here as we see in the figure. So the generator can be divided into multiple sub-generator blocks, each of them responsible for generating a patch of the full images. And at the end, the generated image is formed by concatenating the patches. And yeah, we use this model a lot, especially if you want to, for example, rebuild reconstruct data or generating data if you don't have enough data. But it should be similar, and most of the time it's like used for a lot for images. Another model which is like very similar, the autoencoders. So classical autoencoders compose like with an encoder that performs the compressor, then a decoder that performs the decompression. Same in quantum. So quantum autoencoders reduce the dimensionality of the quantum states, so with the compression, and in order to encode the information into a smaller amount of qubits, you can use that. Besides being applied for transforming and mapping large problems into smaller quantum circuit equivalents, so can be also applied for denoising. If, for example, you have a data or like for an image that is like noisy or not clear, you can just use the autoencoders or quantum autoencoders to do that, because like they extract the features from the initial quantum state, neglecting the noise. And for the model, there is like different ones, and I mentioned this is like I just selected a few of them based on the papers. Now moving to the application side, but before that, I mentioned like there is a lot of challenges of those models. So we will discuss them first. So the first part, data encoding. I didn't cover data encoding, but as I mentioned, there is like different techniques, but some of them are inefficient. Like sometimes they don't have capturing or capturing the same information that you had before. And yeah, data fidelity loss, that somehow we don't preserve the same information that we have in classical than in the quantum stage. But still, like most of these techniques are kind of like we cannot compare them. Not we cannot compare them, but I would say it's very hard like to find which one is better, because like we need metrics to compare them. For example, there is like amplitude encoding, angle encoding, and other ones. Let's just like give this example, amplitude encoding and angle encoding. So one thing to say about them, so angle encoding, it captures like, or like it encodes into rotation angles. It means like it will use like, if you have n features, it will use n qubits. Okay, this is the first information. Therefore, amplitude encoding, it's like the 2 power n number of qubits with n number of features. For example, if you have 16 features, you can just use 4 to represent them, 4 qubits to represent them. So here it's kind of like easy based on the need of like how many qubits I want to use and how many features I have. So it's kind of like you have the choice to decide. But the thing is like sometimes even with this, angle can be better, but amplitude in some scenarios can be worse. Then you change the data, you have amplitude is better and angle is bad. But you judge based on the performance. Like you go till the end, like for example, if it is classification, you will judge based on the accuracy. But that loop, and there is different things, there is a lot of factors involved. So we cannot assume that this part exactly is like responsible of improving or not. So that's why I would say in the data encoding part, we need more metrics to compare these techniques to find the best one. And probably there is like some like to quantify the information, which is like entropy. Another challenge, which is the algorithmic barriers. So we have barren plateaus. Barren plateaus, usually if you increase the number of qubits and sometimes number of layers, the gradient or the loss gradients vanish as like the circuits become deeper and making the optimization nearly impossible. So the scalability is also a problem. or a challenge. Then the hybrid integration, as I mentioned, so this like the loop between moving from the classical to quantum and quantum to classical, somehow we cannot control it well, so we might be losing something there. So this is also a challenge. Then another important challenge, which is benchmarks. So we don't have like a standard and metrics like classical. For example, if you go through some data sets, just MNS or like medical MNS, if you go there, you will find like there is plenty of models and there is the accuracy, precision, and different ones. So in quantum, this is missing, I would say. Like if, for example, if I want to compare different models, the way how are implemented is different. Also, like some rely on this metric, some they don't, and other things. And it's very hard to do that. And also we need to define more metrics, especially like from the interpretability and explainability part. Then another part which is like the quantum advantage. So right now we are still exploring. So, but yeah, sometimes like we use like what we are looking for quantum advantage, but still like the word is not really defined. Is it like in the speed up or like in the computational resources? So we are still trying to explore that or like define that. What's that defined? It will make it easier to say what is quantum machine learning or what's like the benefits of quantum machine learning. Another challenge, which is the noise and robustness, which is sensitivity to the noise. Like if you are using hardware, it means the performance will get like lower a little bit. And we have different error mitigation right now. Like even there is like some nice libraries that can help you integrate that. But still, like which one is better for your model, you need to try. And also sometimes it's like they are quite expensive, like from the computational resources. Then one of the biggest problem is the circuit design. As I mentioned, like sometimes, of course, like from the paper perspective, some of them, they show you the step, how they design, but it's very hard to design a circuit, to be honest. Like you start, okay, you have Hadamard, you put it, then you add this, you put it, but you don't know like what you are doing exactly. Sometimes you feel you're just adding gates and trying. So this is understanding that black box that answers how it works, in which case is like contributing to the performance exactly a problem. And this is what we call like manual architecture design. You do it like by yourself or like just like manually adding this and this. Of course, sometimes it comes like from the theory. You can just develop a Hamiltonian, okay, and you do all the calculation, then you somehow map it into the gates and introduce the circuits. But yeah, it's based on the objective. For the application side, it will be like more, I would say, you need more automation tools that find the best circuit for you. You don't have to do that, since there is plenty of the techniques, but still it's like a challenge. Then the last challenge is the hardware. Of course, there is the qubits constraint right now, even though like with some companies, like we have like around 265 qubits, but still like from like moving from the software side, which is designing the algorithm, to the hardware, it's also something, because somehow you need to make sure that your algorithm or what you are proposing or what you are designing is like suitable for that hardware. So sometimes you try with different type of hardware, superconducting, trapped ion, and different ones. Sometimes it's suitable for this, sometimes it's not. So you need to take that into consideration. But still, like with all these challenges, we are still exploring and doing kind of like different application, like for example, cybersecurity. We do like intrusion detection, malware detection, user authentication, and for the healthcare, like can be used like for medical image analysis. There is like different quite technique for imaging coding, also like for detection part, like tumors detection, abnormalities in radiology scans or CT scans. And it can be also used for disease diagnosis, for material science, has like a strong potential. Can usually for like quantum computers are naturally kind of like more suitable to model physical systems. So this kind of application can include material properties, understanding the structure, improving characterization methods. Just like an example, like it can help simulate how new materials behave under stress or temperature variation, which is like a key for designing better materials. We have also climate modeling. It can help handle the data sets and highly nonlinear system, especially if we are talking about Navier-Stokes equations and different systems. Then in the finance, there is like a lot of proof of concepts, like including fraud detection, market prediction, like where algorithms attempt to identify signals in noise time series data. We have risk management, portfolio optimization, credit scoring, and different things. And lastly, there is the optimization parts. So here also has like some potential. It can be used like in different, even in the fields that I mentioned before, but it's more into the transportation part. Like we have vehicle routing problem, travel salesman problem, and too many things. How many minutes I still have? Yes.
15 minutes more.
Okay, so I can just cover. Okay, I can cover the some finance application. Then based on the time, I can cover another thing. But yeah, just tell me once I have like 3 minutes left. Okay, so for the finance application, as I mentioned, it can be used like for different ones. This is just like an example. So it's called like portfolio optimization. So in this work, we have proposed a framework for exploring quantum circuit parameters. For like we use two algorithms, variational quantum eigensolver, because like this is kind of like an optimization problem, and the other algorithm is quantum approximate optimization. So for each quantum circuit architecture, we try to various range of like other like encoding and insights. But yeah, the main thing is to compare the predicted ground state energy to the estimated classical solution. And our findings reveals like an interesting correlation between the quantum parameters and solving the problem. Yes. So, but yeah, usually for portfolio optimization, you start like from a data set, which is most of the time we use Yahoo, which is a bunch of like stock markets. Then you try to optimize which one is like the most optimized circuit that you can invest. Then you try to calculate the probabilities of that, which is like kind of like you map it into a loss function and try to optimize it over time. Then once it's like converging at the end, you get like the bit strips. Then that represents, with like high probability, represent the most optimized portfolio. The problem with these problems is a kind of like very hard to interpret the results. Like sometimes it can be wrong unless you have some finance background or someone, a collaborator that is working on the finance side. So sometimes I would say like if in the finance side, I would say choose wisely the problem. So if you are not familiar with the problem, it can be quite challenging. Another work which is like fraud detection. This one I would say in interpreting the results kind of like easier comparing to portfolio optimization, because it's a classification task. So you can rely on all the classification metrics. But the problem is like with the financial fraud detection, it's like unbalanced data set. Only a few fraud samples, and most of them are non-fraud. So you need to not rely only on accuracy, but more on F1 score and recall and precision, like the true positive and true negative. So here in this work, we propose like an architecture to do fraud. But the problem is like we tackled is like usually for the quantum machine learning models are not secure and private by default. And if you are working on the application side, sometimes your customer can be someone that, like, for example, here, if we are talking fraud, it can be bank. So we are dealing with sensitive data. And if we are dealing with sensitive data, we cannot just use the model directly and enter like all the details. So it can be a bad thing that your data will be like available for everyone, or like a hacker can attack the model easily and take the data. So for that, like sometimes you need to add or design your algorithm or your model in a way that is like private and secure. So this is one way. So we use quantum federated learning. Quantum federated learning, it means that you have like multiple users and they can use the same model without sharing their data. They can share only the parameters. For example, I built a quantum machine learning model. Then there is like different banks, they want to use this model. I am telling them like you can use the model without sharing your data. You just need to share with me the parameters update, so I can just update the model based on the need of the data or like the customers. Yeah, and it was working, like the high accuracy for all the clients. Another application which is like financial markets prediction. Here it's a little bit kind of like different things all together, which is like quantum attention, deep Q networks, which is like a little bit of reinforcement learning, and also a quantum circuit. So here we use the VQC inside a traditional deep Q learning. It's always like hybrid. You just start from a pipeline that is like has been done classically, then you start like switching step by step into the quantum side. So here there was like a traditional deep Q learning. Then after that, we start adding changing the agent into quantum. And for this market prediction, it means just like, oh, you need to know like if it's like the price of the stock will get like higher or not. Sometimes it should be specific because it's a time series. For example, day 1, day 2, day 3, and you start predicting the price of each day. Here in this, we use like a S&P 500 stock market. It's also from Yahoo Finance. You do the pre-processing and use it for the model. And the thing is, like in this, besides like like in the prediction tasks, especially for finance, beside the loss and other metrics, you need to check like the risk-adjusted returns, and with other metrics like something like called Sortino and like other finance metrics. That's why like sometimes it is important to know like how to evaluate the performance of your task in the application side. Yeah, and also it was working. Then yeah, Another one, which is like loan eligibility prediction, which means that based on some data, it's like also for banks, you can just decide if this person is eligible to get a loan or not. Sorry. You start with designing the circuits, as I mentioned before. Okay, you have a whatever model you try. For example, here quantum neural network. You have a tabular data of this like features and the labels, which is like yes or no, like for the eligibility. Then once you apply that or like you implement your model, it's not working or like the accuracy is low. That's why somehow you need like, especially in this kind of application, it's kind of like you need always to adjust, like do a lot of adjustments and like tweaking to make it suitable for that application. For example, here there was like overfitting, so we had like to like boost like the performance using a dropout mechanism, which like just like, okay, we have a very expressive circuit, like deeper. Then at some point we start like mapping the gates into zero to drop them because we don't need them maybe in the 50th iteration. The model has already learned, then that will cause only overfitting or over parameterization. Yes. Then there is one more application, but I think it will. How many minutes I still have?
5 minutes.
Okay, then I will just jump to the conclusion. Then we can discuss like in details any of those application or other application. But yes, like one thing about quantum machine learning for the application side is like most of the time people are asking if I can do this using classical machine learning, why I would need quantum machine learning? And this is, I would say, a very important question. But then now we are still looking for the answer because like, of course, like portfolio optimization can be done classically. This fraud detection can be done classically. And of course, the performance probably is better than the quantum in most of the time. So it's like finding the right problem for the quantum machine learning models is the right answer for that question. It means okay, and this setup is like classical is better, if the objective is to beat classical, I would say no need at the moment. Just try to understand the behavior and how to design better models, how to make sure that this quantum machine learning models can be applicable to real world application. So yes, how to find the right problem. So this is also kind of like a very general question, but yeah, it's good you start with something simple, then you start increasing the complexity of the model. For example, in finance, okay, we have this, is it like working? So you need first like to put some question. First thing, designing finding a problem, it can be simple at the beginning. Okay, designing the model. Second, third, evaluating. This is important. You need to list all the metrics that can help you evaluate the models. So there is the performance models. For example, classification, I will put all. I cannot rely only on accuracy, and this is a mistake. I need to put them all. Accuracy, precision, recall, F1 score, area under curve, sensitivity, all of them. Okay. Then another part which is right now very important, especially for the application, is like the expressibility and interpretability. It means that like we need to understand how this model is taking the decision. This is why like I can trust it. Like for example, for fraud, I don't know how it's like, okay, it's kind of like I design an algorithm and I'm getting an accuracy of 90% or 95%, but I don't know how exactly that circuit or that model is taking the decision. So if I don't know exactly, it means that I cannot trust the model. So for that, we need interpretability and explainability metrics. And of course, like one way is you just to start from the classical. There is like the field is like quite old, so you can just like go and see what kind of metrics we have in classical, then calculate them. If they work, it's good. If not, try to find a quantum version or equivalent in the quantum circuit. And this is what people do. There is a lot of good papers, I would say, for the interpretability and explainability. Okay, and this is the evaluation part. Okay, if I can, like, I have all the metrics and the performance is good, it's good. Then I will start doing more analysis to find, like, increase the complexity of the problem, see what is the limit of this model to do this task. Another part, if it is not working, the performance is kind of lower, you need to start injecting and integrating different techniques to improve that. And as I mentioned, like you can just use circuit design, maybe but yeah, you need first to find like what is the problem exactly, and it's very hard to find it because like it's kind of like you have a bunch of things working all together. So if you want to find the problem exactly, and you cannot do ablation studies, so it's very hard to locate exactly where is the problem. Is it in the encoding? No. Is it in the circuit itself? Is it in the measurement basis that we are using? Is it in the loss function? Is it in the circuit, like the number of layers, the depth? There is like plenty of questions you start putting. Okay, and you just start one by one, since you don't have that answer. Okay, let me try this. So I will just change this and change this one at once. So for example, the encoding, I'll try bunch of encodings. Okay, then I will identify that this one is better. Then I will move to another thing and change it and find until like the model is improving. But sometimes there is like some ways or tools to find the problem exactly. For example, for Barron plateau, you can just calculate the gradient variance, then you see if it is not improving, then you have barren plateaus. But yeah, some of other problems you cannot just like identify them. Then yeah, this is the steps like usually that you need to follow for the application side. But yeah, it's always based on the objective. It is just like a proof of concept that quantum machine learning can do this, or is it like you want to do like a proper benchmark against like some other algorithms or even classical, but you need to find the right metrics to compare and make it like fairness. So fairness is means like, for example, if your objective is just to compare classical versus quantum, you have a quantum model QNN with 5 layers, and you need to use a very equivalent to this one, like same number of parameters. Hence, you can compare. For example, you have like NNNs like with 5 layers as well, same number of parameters. Even with this setting, it's very hard to compare, but at least somehow you are kind of like in the edge of the fairness of these models. Otherwise, like sometimes you just go to the weakest model in classical for just like, I won't say weakest, just like very simple one, random forest. Okay, then I will compare it to a QNN with 16 or like just like 10 layers. So, and I will say like, oh, QNN is better. It's definitely better. Like you have a lot of layers, and so you cannot just compare to something like very different. So somehow you need to make it fair. But in another way, I would say like comparing classical versus quantum is kind of like challenging because like we still have that loop. So somehow two models are kind of like in different paradigms and different settings. So make it like very challenging to control each model or each component in the model itself. Then yeah, that's for the application side. Yeah, for the conclusion and takeaways. So as I mentioned, quantum machine learning combines like quantum computing and machine learning to explore new computational possibilities. We are still trying to explore them. How does it work? We have the hybrid models, encoding, parameterized circuits, and the optimization part, which is done classically. Then, as I mentioned, like one of the example like QNN, then where quantum machine learning can be applied, it can be applied to any of the field. But yeah, it's based on your objective. If it is just like finding what is more suitable for quantum machine learning models, mean finding the right problem, it's not easy, but yeah, this is itself a objective or a research direction. And what's holding us back? There is the noisy hardware, limited qubits, encoding challenges, and clear quantum advantages for many tasks. So that lead us sometimes to the hype. Quantum machine learning can do this and this, but sometimes we need to know the limitations. And yeah, quantum machine learning right now is not faster by default. And it's not like we are trying to replace machine learning with quantum machine learning, not at all, at least from my perspective. We are using a lot of techniques from classical. So you just like think of it as like another direction. You can use this and you have another way to do things. And we are still trying to explore that other way, how it works and what can bring into the table from utilities and improvements. And yes, that's all from my side. Thank you for your attention.
Thank you. Thank you, Mark. Thank you. So please, I have many questions for you. Can you go back a little bit on the application side? Slide, sorry.
Yes, once again. Yes, this one.
No, for the financials.
Yes.
For the financial slides, sorry.
Oh, for the
Yes. When you put 4 different applications.
yes, here.
Right. So right here I have a two question. For the last article on loan eligibility. So here from the article they did not run on the real hardware, right? They just use the noise models.
Yes, exactly. So yeah, we didn't run on the hardware itself. We just like sometimes we don't have access to that. So what we do is like we simulate the noise and try to run the same model on a noisy environment, which is a little bit equivalent to running on the hardware, and see like how is the performance is. Most of the time is like there is like some degradation, like for the noise models. So usually there is like cross operators which come like from the theory itself, and we try to map some of them. We call them like noise challenge, bit flip, amplitude damping, depolarizing, phase flip, phase damping. So, and they have like a proper equations how to inject them, but like in the implementation side, it's getting kind of like easier because you can just like use pre-built functions from different either Qiskit or Penalty. Yeah. So regarding the performance, if once you inject those noise into your model, it means that you don't have that perfect environment, which lead like to some degradation in the performance. The main thing is like you need somehow that your model is kind of like it's still working in a reasonable performance, I would say. So maybe it's still like working at 80%, 85, 90%. If it is like with 95 or like there is no degradation, it means that your model, how you design the model is robust against noise, which is good. Like once you test it on the hardware, probably you will have the same performance. Not the same, but yeah, because there is the probability, the randomness. So, but yeah, somehow kind of like similar. But the thing sometimes, if you don't have that good performance, that will lead us to the mitigation technique. You need to think either like design a better model that's somehow robust against noise, or just inject also the mitigation technique. Mitigation technique is another thing, but yeah, it's just like you need to inject them to somehow get back like the loss of the information that you lose it from the noise. But another aspect, especially for quantum neural network, is sometimes when you inject the noise, your performance gets better comparing to noiseless environments. Means like you can run it on a simulator, it gives you 80%, then you can do the noise injection and everything, and you get like some 90%, 95 or something better. Yeah. Why? There is some papers that try to understand the behavior, but yeah, sometimes noise is good for the model, especially for some sort of application. Another thing that we can somehow explain is sometimes that the model learns how to deal with the noise. So it's kind of like it's getting better. So I'm getting better in this environment. So it's the same thing for the model.
But so the noise model did not take into account many aspects of the quantum hardware. So
No.
are you planning to run it in the real hardware in the near future?
Yes, definitely. All the application right now, from the application, at least I would say, we are trying to get like one of the configuration run on the hardware itself because it's good. But yeah, then there is also like fake backend. Somehow it's like a simulator that somehow has all the information that of a hardware, then somehow simulate the same behavior. It also can be used, but I think like for the noise model somehow is reliable because like it somehow simulates similar noise in the devices. It's just like it depends based on the device. For example, from a company to a company differs from like the hardware that they are using, or like the chip, the processor, the quantum processor that they are using is different from another. Then also another thing that you don't in the device beside the noisy environment is kind of like the mapping. So we have the physical and the logical mapping. So sometimes, like Hadamard gate exactly, if you want to run it on the hardware itself, it's not Hadamard. This is just for us. In the hardware itself, it's a bunch of operations. And sometimes that like mapping can be very costly, and that's why like you get like a lower performance. So there is like a lot of factors involved in the hardware beside the noise. But yes, for the application, definitely we need to have done the hardware results, and we are planning to get most of the application to run them and implement them in the hardware.
Okay, so one question on the financial market prediction. What is the accuracy that you expected that you got for this model using the quantum computing?
Yes, so for the prediction, it was like we don't use accuracy, we use the loss.
Yes.
MSE and the other type of loss, R square. I cannot remember the value exactly because it has been a while, but
Yes.
it was good.
Around 18? 80, sorry. Around 80 or 90% of accuracy. Do you have a number?
No, like it's not accurate. Yeah, so as I mentioned, like prediction, especially for time series, because it was over the time, it wasn't. We don't calculate the accuracy; we calculate the loss, and for that, like I would say, kind of like if you want to put it in accuracy, it was kind of like 90 or something. But yeah, I don't remember the details, the values, but it was quite good. Like you can somehow rely on that value. It was doing the task good, not perfect, but good.
Okay, thank you. So for the portfolio optimization, how many assets did you use? That you able to use for simulating?
Yes, so for this work, it's like with because like it's from my team, I cannot remember the details. Probably they use 4, but we have a recent one that's also this year. We use, I think, yeah, we use 4 assets per qubit when we tried like to increase that. Like we did couple of studies. It means like how we can, how many assets we can represent with 1 qubit. Then we kept increasing. I think one of the best configuration, one assets per qubit, and we use, I think, 4 qubits, 8 qubits at maximum, if I remember well.
Okay, so that means that you can use 1 qubit for multiple assets, right?
Yes, there is a way, but the thing is, like as I mentioned, with portfolio optimization, that this has been done like from my team. I wasn't like I didn't join yet the group, but recently, as I mentioned, we just kind of like discovered that somehow, even if the model is performing well, means like, okay, because it was optimization, the loss is converging and everything is good. Based on finance side, the choices or like the configuration that the portfolio, the optimized portfolio that's given wasn't that good from the finance side. It wasn't that like the best one, the optimal portfolio. So that lead us that we need, besides like performing the task using quantum, of course we get like some probabilities, but we need somehow to inject or integrate some techniques to somehow make the decision towards the quantum, towards the finance side. Because okay, we have a bunch of bunch of like probabilities that this is the optimal, but if I just like rely on the model itself, it won't give me the optimal for the finance, for example, from the finance background. For example, this one is optimal in the calculation, but in the finance, if I use this portfolio, I will lose a lot of money. So somehow you need to integrate some calculation that comes like from the finance to make sure that it's kind of like a combo or combination between the quantum probabilities or the quantum choices with like the finance indicators that give you a best option.
Thank you. One last question. When you talk about the different quantum machine learning model, and we need to, for all the model, we need to use a classical optimizers in the end to find the lowest point, lowest energy, isn't it?
Yeah, so that's the part of the optimization. I didn't cover that in details, like I said, like the next speaker probably will do. But yeah, so for the optimization, it means like, okay, you do the post-processing, everything you calculate, like at the end, it's kind of like classical. You calculate a loss function, okay, which is like just like from the predicted and the actual value. Then you see that your loss need to be more optimized, and you use an optimization technique, which is like there is plenty of them, like gradient descent, which is just like the second the derivative of that loss comparing to the parameters. Means like I write the lossing function of the parameters and I try to optimize it. It means that I need to find the best parameters, tunable parameters for that. So I calculate, then I update those parameters. For example, I started with the rotation of pi, then I calculate the loss and everything. Then I do the optimization part. It started like pi multiply by something, or like it can be lower, or so this is how the optimization part.
Yes.
And
But that is a problem. We cannot find it's very hard to find the global minimum. So my question is, why don't people use, for example, quantum algorithm to minimize to find an OS point instead of using a classical optimizer?
Yeah, so there is this like I think there is a paper about like quantum gradient, quantum natural gradient or something. I can check and share it later. They tried like to use a kind of like a quantum version of that. They showed that the landscape, like the loss, was converging to global minima instead of local. But I don't know about other techniques. Probably, I don't know. I will say like you cannot complicate things and use another quantum algorithm, let's say quantum optimization algorithm to do the optimization of your QNN. So that will be a lot of circuits and probably a lot of computational resources and a lot of noise. So I'm not sure how will that lead, but yeah, you can just try and see. The other part, as I mentioned, probably there is some techniques that they are trying to make the quantum version of the optimizers. As far I know, I think there is the QGN, quantum gradient natural something. Yeah, but I don't know much details about other techniques.
Okay, thank you. Any more question? Okay. Thank you for your effort. Thank you for joining us for this very beautiful event. I'm very curious about your research, so we keep in touch. Please. And I think I'm closing the morning section for now, and we will see together in 1 hour maybe.
Okay, then thank you so much for the invitation. And if you have any questions or you want to know any details, you can contact me. Have a nice day.
Thank you.
Bye.